Hello my dear students, in this particular lecture we will be covering the different modes of operation of DC motor drives. So as far as DC motor drives are concerned, we are almost familiar with the different quadrants of operation of a DC drive or a simple drive. So now we will be exploring the different regions of operation. That is the first quadrant, that is forward motoring. The second quadrant, it is the forward braking. Third quadrant, reverse motoring, and the fourth quadrant, reverse braking. Now this is applicable to all the drives, but in case of DC motor drives we are going to explore the speed torque plane, and we will study each of the operations, how they work, the different modes of connection that we are going to study. So let us proceed. So in the last lecture we have covered the series machine as well as the shunt machine, their basic speed torque equations, and how you can control the speed, that is the armature voltage control and the field current control, when to operate in a constant torque region, when to operate in a constant power region, that we have studied, and we have seen the graphical characteristics. So now here we are going to discuss the different operational modes of the machine. So in variable speed applications, a DC motor may be operating in one or more modes. So what are the modes? Motoring, regenerative braking, dynamic braking, plugging, and obviously it is going to operate in all the four quadrants. So now I will just give you a recap. So this is all the four quadrants of the torque speed plane. Right? So you see here, this is forward motoring, this is forward braking, this is reverse motoring, and reverse braking. So this will be the output of your motor drive. No matter in which way you are going to control, this will be your output. That means in the braking region it will be this or this. In the motoring region either it will be in this quadrant or this quadrant. Right? So then this is a schematic diagram or a circuit diagram of a separately excited motor and a series motor, and both the machines are connected in motoring modes. So the arrangements for motoring are shown in the figure, and obviously the back EMF EG is less than supply voltage VA, obviously, because EG, rather it should be EB or the back EMF. For generator it should be EG, for back EMF it should be EB. So let us replace it by EB. Here also it is EB. Here also it will be. So these are the nomenclature conventions, right? So EB is equal to, what is the supply voltage? It is VF minus, or sorry, it should be VA minus IAR. So obviously EB is less than VA. So in both the cases it is true. The only difference is, in separately excited machine the field circuit is separated. It is a separate. and the motor develops the torque to meet the load demand. So here both the armature and the field currents are positive, right? So the output should be a positive torque and a positive omega. That means if you see the speed torque plane, this is your output. It should be in the first quadrant operation. So both are positive. So this is positive and this is also positive, right? So now next comes the regenerative braking. Now before going to regenerative braking, why should we go for regenerative braking? That is our matter of concern. Okay. Why should we adopt regenerative braking? So let us start with a very basic example. Suppose you are having a train, right? For simplicity, I will make it like this. And the train is moving on a track. So suppose the motors are connected to the wheels and the direction of the torque are given by the arrows like this, right? So now let the acceleration in the forward direction is denoted by F, and the torque is denoted by tau, because it is the acceleration, and corresponding to that there should be an angular acceleration or an angular speed. It should be omega, right? So now as it is moving forward and the entire thing is having a mass m, and if you consider the equivalent moment of inertia, it is j for angular motion, right? So now what is happening? The motor torque, if it is tau m, it is equal to the load torque tau L plus j d omega dt, right? So what type of load is subjected to the motors? So from our basic sense, the load torque tau L it should consist of the weight of the motor itself, it is Wm, and the weight of the coaches. This is one part. Number two, what is another part? That is the load, means load will always oppose the motion, right? So the weight will always oppose the motion. That is very true. So what else will oppose the motion? The frictional torque or tau m, that will oppose the motion, right? Number 3, what else can be opposing? When it is moving forward, the wind is flowing in the opposite direction. So the windage torque will be there, which will oppose the motion. And your motor torque, tau m, should be satisfying at least all these things. And minor torques are also there, which needs to be considered. But these are the major opposing torques, which the motor torque tau m has to taken care of. And all these opposing torques are collectively called tau L or load torque. So if tau m is equal to tau L, at that point what will happen? You come back to this particular equation. So if tau m is equal to tau L, then obviously d omega dt, that will become 0. That means your omega is equal to a constant k. That means your machine will, or the train will move at constant speed. I hope you are able to visualize. But what is my requirement? You have to be very careful when you are designing this entire thing. First, you have to be aware of what you require. So you require to accelerate the train with a linear acceleration of f, and an angular acceleration of the wheels in that case will be alpha, which is denoted by d omega dt, right? So your torque equation should be not this, rather your torque equation should be tau m is equal to tau L plus j d omega m dt, and in place of d omega m dt, obviously I can write alpha. So it should be plus j alpha. So obviously in that case it is very evident from this equation, in order to obtain this alpha, your motor torque has to be greater than the load torque. Only then your total tractive load, your entire train, that will accelerate, and the angular acceleration will be alpha, the linear acceleration will be f, small f. So this is the condition, or rather it is the initial condition. Now suddenly what is happening? The station is approaching, and the driver in the station, or sorry, the driver in the train, he is trying to apply the brakes, right? So as soon as the brakes are applied, these are the mechanical brakes. So what will happen? So the motors which are connected to the wheels, let us draw it again. If the mass is m, now the brakes is applied. Obviously when the brake is applied, the motor torque will be reversed. That means in the first quadrant, if it was positive, so it was during motoring operation, it was in the first quadrant. Now it is in the opposite direction. Initially it was in this particular direction, but now it is negative. So your quadrant will be shifted because your sign has changed of the torque. At that particular instant, what about omega? So the angular velocity or the rotation of the wheels was in the clockwise direction. So it was positive. But when the brakes are applied, what happens to the angular speed? The angular speed, its value will reduce. When the value is reducing, what will happen? The entire train or the entire motor RPM, that will become low and your train will slow down. It will slow down. Now as it slows down, what happens? Your speed or the direction of the rotation, that will be in the clockwise, that is in the original direction, but the value will become low. Sorry, in this here in the x-axis it will be torque and the y-axis it will be speed. So let us draw this again. So if this is the speed torque plane, if this is the speed torque plane, the torque becomes reversed, but your omega, it will not reverse, but it will slow down. So your omega is positive and your torque is becoming negative. So what does this indicate? So it indicates that the operation has shifted from the first quadrant, that is forward motoring, straightway to the second quadrant, that is forward braking. This phenomenon is called electric braking. But there is one disadvantage. So as the motor slows down, if you see the train wheels rather, so what will happen? Initially the torque was in this direction and now it has reversed. So the train is trying to stop, right? So what about the friction? So there is huge friction between the wheels and the rail track, which is dissipated in huge form of heat. Immense heat is produced. So this entire, so I can say this entire electrical energy which is there in the machine, when the machine is slowing down, this entire energy, massive quantity of energy, should be wasted and dissipated as heat in the railway tracks. So there can be one solution. What type of solution? Let us put it in this way, that in this era of energy crisis, can we afford to waste electrical energy? Are we supposed to waste electricity? An answer will come no. So obviously, in the mind of the electric drive engineers, an idea popped up that what if we can save this energy? What if we can save this energy? If we can save this energy, then for a particular train, it will slow down repeatedly. When the station is approaching, there will be numerous stations, and every time when the locopilot is applying the brake pedals, immense energy is wasted. And if we collectively see this amount of energy for a single train, the value is very, very high. It is very, very, very significant. And the cost of the electricity which is being wasted like this, that cannot be ignored at any cost. And if we can save this amount of energy, we will be able to save lots of energy. Not only that, we will be able to save money because your electricity charges will become low. Your total electricity cost will become low. So this is a very good idea or objective oriented idea that came into the mind of electric drive engineers. So what they did, they devised one mechanism so that this electric power, instead of getting wasted in the railway track, they will be rather sent back to the power supply. That means if we can somehow reverse the power flow or reverse the direction of the power flow rather, then we will have an opportunity to send back the power which is going to be wasted, to prevent it from getting wasted and send back that power to the power supply. Right? So basically, we are doing braking. That is very true. We are doing braking. But what type of braking? The braking occurs, or the braking of the motor occurs in such a way that the energy is not wasted. We are preventing that. So wasting the energy, and to prevent that wastage of energy, it is very much suggested that you are generating energy. You are generating that amount of energy. You are not wasting that energy. So not wasting any energy is equivalent to generating energy or regenerating energy. So that's why this braking process is titled as regenerative braking. This is known as regenerative braking. And remember, this regenerative braking is a groundbreaking revolution in electric drives industry because it is saving power from getting wasted, and it is reducing the cost of operation of an electric drive, which is very, very important. So that can be achieved. So this is the main motto of regenerative braking. So this is the main ideology behind regenerative braking. So let us stop here for today. In the next lecture, we are going to go deep into regenerative braking and have a fruitful discussion, and we will see that how they are connected, how the machine is connected. For regenerative braking, what are the modifications in the machines has to be made, that we are going to study along with the different operational characteristics. So see you in the next lecture. Thank you.